And just so you know, I'm not gonna put this one. I'm not gonna record this into the cloud. I'm gonna record it into um, my laptop, and then I'll post it up in YouTube, which is the only way to use Zoom, unfortunately. All right, let's go to. I'll be using this whiteboard a little bit later.
Looks like Quinn's here.
Okay. Let's go to Keynote. Did you say that Quinn is here?
Yeah.
Okay. Can you see if you can make her a co-host?
I don't believe so.
Okay, let me see if I can do it. Quinn, where are you at here? Okay. Okay. All right, Quinn, you're a co-host, and that means that you also have you could turn your microphone, and you could turn other people's microphones on and off as well. So it's a little bit different from conferences. Tell me when Kendra gets in. She's around somewhere. She was just emailing me a minute ago.
Okay.
Okay. So let's get going with the now. Can you guys see the outline for today and Area 51 image?
Yes.
Okay, good. All right. Hi, John. Let's take a look at some problems that I like in the textbook. So let's see if I can do. Here it is. Okay. All right. So let's share this. Okay. Can you see chapter 9.6, center of mass?
Yes.
All right. C. Very good. James Engelmeyer, are you doing Chrome, Google Chrome now, or what? I don't want to hear any more about this Microsoft Edge business. Okay. Oh yeah, so yeah, I guess so. That's right. I guess you're using the app. Okay, Carlos, I have no idea. The morning session is the one where I've designated to be attended. So if you're in today, you're in. If you're not, you're not. But I hope you did hand in your homework. Now I want to go over some problems in here that I like, and this whole business of like this cat and the or the motorcyclist taking a jump. We're going to talk about that, and the big distinction is between internal and external forces. And when there's no external forces acting on a system, like the two spheres in the homework, only the interaction forces, those are internal forces to the system, the momentum is conserved. But if you have something external like gravity, then you don't have conservation of momentum. All right. So, but what I want, there's some problems down here that I want to show you. And I've highlighted some stuff. Let's see. Yeah, so I've annotated some stuff here for you, but they start looking at the center of mass a little bit differently. So review that, and and then kind of triangulate from the way that I described it and the way that the textbook does, and hopefully that'll be helpful. Here's the basic formula for center of mass down here, by the way. Basically, for each component, so for X components, you go the mass of the object times its X component plus the mass of the next object times its X component plus the mass of however many objects you have times each of their X components. Add them up and divide by the total mass. That's 1 over m out in front. And then you do the same thing for the Y component of the center of mass. And they kind of show you how to do it down here in these. Well, these are this is graphic, but if you think in terms of components, here it is. You know, here's what I was just telling you. So for the x component, you've got this formula, for y component, this one, and that's basically how I figured out the equation of motion for the center of mass in the homework, which you weren't required to do, but it was something I did ask you to think about. Okay, velocity of the center of mass is just d by dt of all that junk. So the d by dt goes through all this summation business and basically just hits the vector r subscript j. And j is the subscript that counts up the number of objects that you have. So like for our homework, j would go from 1 to 2. It was pretty easy. You don't need all the summation notation for something that simple. So v of j, vector v of j is basically d by dt of vector r of j. So, and it goes the same way by components. Now there's some problems down here. This one is something that we talked about, the center of the mass of the Earth-Moon system, and they have a nice diagram here. It's not to scale for the distance between Earth and Moon. That's way too close for the Moon. That would make the Moon look like a Death Star hovering over our planet for our destruction. But the position of the, here you can see 4,640 kilometers from the center of the Earth. So that's somewhere out here. The radius, the full radius of the Earth itself is about 6,371 kilometers. So the center of mass is, as I said before, is located kind of down here. Now, here's a problem that is nice for you to work out. And this one, they actually give you the solution, 4.6 kilometers. Go ahead and try this one and verify it for homework. That's a good one to work on. All right, now this one looks nice because it has to do with all this dipsy molecules and stuff. And I know a lot of you are chem and biomed majors, but unfortunately, there's a killer sentence down here after all this work. There is no meaningful application of the center of mass of a unit cell beyond as an exercise. So for that reason, we're going to bypass this one, right? So it's just it's a grinded out thing, we're not going to mess around with. Now, this is something that I want to talk about in detail after we go through all the problems that I like. And that is, if you have something that's like a planet or an idealized planet, I guess. Well, even a regular planet, you have to know a lot about the variation in the density and stuff of the planet. But this is how you figure out for an object with a continuous distribution of mass. That's how you figure out the center of mass position, relative to whatever your origin is that you just describe. And it'll always come out, it'll always, for a spherical planet or a spherical moon or something like that, it always comes out to the center or pretty close. But now for the Earth-Moon system together, so integrating over all the masses, including the Earth's mass plus the mass of the moon, then it does move it off the center of the Earth's mass. Okay, so center of mass of a uniform thin hoop. Now, this is an important example. I want you to study this one. And we're gonna talk about something a little bit easier than this. Basically, it's a spherical coordinates, polar coordinates, I guess, polar cylindrical coordinates, with theta and r being your main two. Well, r is not variable. And that's why you can make it a single integral here. So this is for a thin hoop, okay? The center of mass, find the center of mass of a uniform thin hoop or ring of mass m and radius r. Now, uniform means it has the same density for every inch. So each little element of mass, each little pixel of mass here is going to be some density times the length. In this case, it's a linear integration. That's why the word thin is applied. When you see the word thin like that in this context, that means that that you could treat it as a one-dimensional problem. So ds would be r d theta in the cylindrical coordinates, and that's how they set it up here. Okay, so here's down here, ds is equal to r d theta, and then you just integrate over theta, and it's pretty easy. It's r squared sine theta j hat, and you integrate over theta, and guess what you get? You get all zeros. So it looks kind of hairy here. I mean, this is kind of bodacious up here, but it works out to be a pretty nice one. Now, what we're going to do a little bit later is do something like a long stick, a thin stick, or a thin rod, as they say. All right. So here's discussion of the conservation of momentum. And this is the key: no net external forces acting. All right. So when we get back to the motorcyclist in a few minutes, I'm going to discuss that a little bit more. In the absence of an external force, the velocity of the center of mass changes. And that's what we saw, or that's what I displayed to you in the early session. You know, that kind of magenta colored dotted line through the middle, it just went straight on. But it was a straight line before interaction, and it continued along the straight line after the interaction. All right. And so the velocity of the center of mass never changes. It's always, it was downward and slightly to the right. Right now, there's some more examples and problems I want to point out to you down here. Okay, I'm not going to mess around with that fireworks business, so you can go ahead and bypass that. So here's a summary and conceptual questions. Okay, here's a nice little workout, 3-point masses. Okay, a little and don't forget to convert to grams. Actually, you don't need to. I mean, this could be 75 metric tons, 150 metric tons, and 100 metric tons. And the same, oh, this is a 3, 4, 5 triangle. Interesting. Anyways, so, no matter what the masses are here, if they're the same ratio, then you'll have this position for the center of mass, negative 1.23 centimeters and 0.69 centimeters. Okay, now this one here, 2 particle masses, M1 and M2, separated by horizontal distance. That one's pretty easy. This is the one that I want you to work on. This one's a little bit tougher, but you guys are pretty good at free fall, and these are straight free fall problems. So it's just y equals 1/2, gt squared, because there's no initial velocity. You're dropping it. Yeah, you let it go from the same height, but at different times. So you have to. So go ahead and work on that as a study problem, and we might talk about that in class in our first session on Thursday. Now, 2 particle of masses M and M2 uniformly in different circles of radii R1 and R2. Definitely take a look at this one. And this one also has the answer. And I believe I have an annotation. Yeah, try this one with M1 equals 1 kilogram, M2 equals 1.5 kilograms. Just to, get a feel for it instead of this stuff. I mean, this stuff is already given. But this will be a good exercise to put together positions of the center of mass. Right now, here's one a 1 meter long rod with 50 centimeters of iron density. Ooh, I thought I annotated this. I must have forgotten. This one. Ooh, I thought I annotated this. Let me refresh my page. Hold on. Come on, baby. Let me try this. Let's see. This one I want you to try, except this one, a 1 meter long rod, half of it's iron and half of it's aluminum, and they each have different densities. Now, the problem with this is they don't give you the total mass, and so you can't figure out the dimensions of the rod. So what we're going to do is assume it's a stick and it has a linear. Let's see if I can annotate this right now. Okay, use linear mass density densities 8.0 grams per meter and 2.7 grams per meter. And I'll show you how that works in just a minute. It's basically the same. It's basically similar to this hoop problem up here. Okay, so this hoop problem, they have a linear mass density lambda. Okay, and that means how many grams are on this thin hoop per centimeter. Okay, and they don't give you the lambda here, I don't think. So it's just a symbolic calculation all the way. It's basically just the mass. Here it is, the mass times the, I don't know if that'll highlight or not. Guess not. It's the mass times the, or mass divided by the circumference 2 pi r. So it's pretty easy. So down when you're down here, they in this the 1 meter long rod, they don't tell you the mass of the rod. All right, they tell you it's 50-50, and they give you these, and this is the real density per cubic centimeter for iron, and also for aluminum. But you can't use this if you don't, because you have to get the mass, you have to multiply by a volume. If your units of density are grams per cubic centimeter. So this problem, I guess they have a typo here of some kind, but we'll get it, right? And I'm going to work that one out myself. I think there's one more down here. Okay, I may put a few more of these on the problems I like list. Whoa. Oofta. This one looks tough. This is, this would be, it'd be kind of tricky. You could do it though. You know, the center of mass of something symmetric like this is going to basically be the center. So the center of each sphere, and then the center of the cylinder, which is halfway down the cylinder and right in the middle, along the central axis of the cylinder. All right. Now, let me pause for questions, and let me pop out the, here I can, where's the chat? Here it is. Okay, ask me a question. James, couldn't you say that the circular cross-section was 1 centimeter squared at any point? Yes, you could, James, but they don't give you that. All right, now if they gave you the answer, you could figure out what the circular cross-section was, because then you'd be able to figure out the volume. All right, but they don't give you, so I have a feeling that maybe they said, yeah, consider it a cross-section, cross-sectional area of 1 square centimeter, but they must have left out that information or whatever equivalent information. But yeah, that would allow you to figure it out in terms of grams per cubic centimeter. Okay, other questions? Anyone? Bueller? Okay, let's stop the textbook and let's go back to Keynote. Oh, I've got to stop my key. This is the key. you have to stop your presentation, and then it'll show up again here. Let's see, where is it? Let's try this again. Here it is. Okay. Now, so we just went over the problems I like. Now, I want to talk about this motorcyclist quite a bit. Okay. Now, this white arc. Hold on. Let me pop out the. I want your questions. So let me open up the chat window. Okay. Okay. Now, if you have a question, I want you to pop a question. And James or Tyler, I want you to activate their mic if they have a question.
Sure.
Okay. All right. So what we've got here is this motorcyclist, and notice that he's changing his position relative to the motorcycle at every one of these strobe photographs. All right. And
Brandon had a question. And also
2.7x. What is that? Brandon, I don't understand. Go ahead, Brandon.
here, you should be unmuted now if you want to.
I was just looking at the rod problem that you were doing using the densities and everything, and I was just looking at it.
Yeah, I see what you're saying. Yeah, it would be something like that, except basically, you know, I don't really like what you got there. I mean, no offense, but what I would do is, you know, just break it up into two integrals. You know, the first 50 centimeters and then the second 50 centimeters, and then just add them up, because that'll, you know, that'll work. Okay, format the next quiz. Sean, the next quiz is going to be next Tuesday, and it'll be a file upload item. Okay, I'm still kind of working out the details of it. All right. Now, Daniel, do you see the motorcyclist now?
I also don't see a motorcyclist.
Oh man, does it? Nobody sees it? All right. Let me stop. Okay, let's try it again. So I gotta go to Zoom, share the screen. Share this. Okay, now do you see it?
Yes.
Okay. All right, good. Now, let me turn on my actual slide playing. Do you still see it?
Yes.
Okay. All right, great. So, all right, so this motorcyclist, if you look at his position, he's changing his orientation of the bike. Now that means he's pushing and pulling and twisting on the bike. All right. And he's, by the time he gets over here to the left end of his arc, he's back pretty much into riding position. But he sure ain't, he's got, I don't know what, he's got his feet over the, look at this. He's laid out here. This is insanity. Okay. I think that's, yeah, that's it. He's laid out right over here on, like, what is this? The third strobe photograph. Oh my goodness. That's pretty audacious. So the point is, he's changing his position relative to the motorcycle. So the two objects, let's simplify it as a motorcycle and a human. All right. Now the center of mass is following this arc. it's exposed to, it's experiencing a net external force, the weight force, gravity, okay? And what obeys the gravitational arc is the center of mass. And that's what this trajectory tells you, right? But the constituents of the system, the motorcyclist and the motorcycle, they're spinning for one thing. And he's changing his orientation to the handlebars in the front end of the vehicle. And it's incredible to think about, but that's just like in homework R, the very brief interaction, the two balls change their position and their relative motion with respect to each other. Right now, momentum was conserved in that one because we didn't have gravity turned on. If we'd had gravity turned on, all of those straight line segments would have to have been a part of a parabola, right? And that's a tough problem. Oofta. But you could do it. And but this guy, he's attached, so he's continuously interacting with the bike, but still his center of motion is moving, just like it were a baseball, right? And just like the center of mass in homework R, it just kind of kept cruising right down the middle there, tilted a little bit to the right, as if there were no bouncing at all. The center of mass doesn't bounce, okay, because it's concerned with the external forces, not the internal forces. Okay, same thing here. Okay, the center of mass, it doesn't care what he's doing to the motorcycle, and vice versa. The center of mass just goes, la-di-da, just like a baseball through the air. So he does a flip. Is that what he's doing? Yeah, well, he's doing a flip. That's right. I mean, he's doing a backflip, I guess, which is kind of crazy in itself. But he's also extending his feet over the. I don't know. Maybe that's how they do it. I don't really know too much about riding motorcycles, but yeah. So right here in the third picture, he goes from having his knees in the regular position in the first, halfway out above the handlebars in the second, and then on top of the handlebars in the. That is crazy. I don't know how he does that in those split seconds. Anyways, that's what's happening. So, so what I want you to think about is this. All right. This motorcyclist, he's got a center of mass with the motorcycle. Good. And we know what the center of mass is doing. But we haven't accounted for the dynamics of him spinning, all right? And the fact that he's able to put relative motion into his own system using some force of his own, and that's an internal force. So that means that you have equal but opposite reactions. So whatever he does, the bicycle does the opposite, all right, in terms of forces. And so this introduces us to the idea of stuff that's spinning. And if something is spinning, it has a completely analogous dynamics to everything that we've studied so far: momentum, energy, F equals ma. There's rotational analogs for all of that, right? And that's what we're heading for. Now I see I have a question here from James. So because he's attached to the bike, their center of mass is what's affected uniformly by gravity? No, what I would say, James, is even if he jettisoned the bike, the center of mass of the bike and man system would still follow that arc. He might jettison he might push the bike upward No, you know, it'd be cool is if he pushed it downward, and so the bike would take its own arc down into the sand pile there, and he would go up above. He'd sail way over the top of the sand pile. All right, but the center of motion would still be on that one parabolic arc, and that's because they left their initial conditions were they were together, you know, where they launched over here in the very first, well, just before the first image. Okay, so so the system in this case the system is defined at the initial conditions as the man and the motorcycle together. And you know, if he later jettisons the motorcycle, there's still their center of mass, you know, just like ours, you know, the center of mass, you know, kept going straight down the pipe there. And even though the two spheres ricocheted off each other, they went elsewhere, you know, but you know, the center of mass just kept cruising right down the pipe. Now, the center of mass is not an object. It's a theoretical quantity or a theoretical construct. So I shouldn't say it goes cruising, but the equation of motion stays the same. That is definitely a kosher statement. Forces he applies on the bike canceled out by equal and opposite. No, equal and opposite, third law pairs do not cancel out because they act on different objects. Okay. He pushes on the bike with a certain force. The bike pushes back on him with a certain force, equal and opposite. But those two forces, they act, one acts on the motorcycle, one acts on the man. So they don't cancel. Okay, it's wrong to think of third law pairs as canceling because they don't apply to the same object. And that's a common misconception. Okay. So, all right. So as I was saying, what we want to think about is the dynamics of rotation. All right. So to get us to that point, I now want to go to the whiteboard and talk about the integral for the center of mass. And then for another object, what we would call a higher moment in the math class of the motion. So let's do, now I'm going to be really rough with this whiteboard. Let's see how this works. Okay. So F equals MA. Can you see me writing F equals MA?
Yeah.
Okay. Okay, good. So let's take a look at this. All right. Let me erase that from existence. Yeah, that works nice. Okay, let's see. So let's do a long stick. All right. Oops, I still have the eraser. Let's do a long stick. Oh, this is a straight line. Good. Okay. And right here, let's put the center of coordinates here. And let's call out here L comma 0. Okay. And this is doing good. All right, this is not too shabby. It's my first time using this Dipsy whiteboard. They're kind of tricky. Okay. Let me move the whiteboard down here a little bit. Okay, let's see if I can move this up. No, I can't. All right. All right, so let's say that let's say that the density is lambda equals 0.0 0.27 grams per meter. Let's do grams per centimeter. Okay. And let's say that the length of this stick is equal to 0.8. No, let's do let's do 0.8 meters. Okay, I'm gonna have to use my digital drawing tablet for this. This will work if I have a digital drawing tablet instead of my trackpad. All right, so let's figure out this. Where is the center of mass? Okay. And we'll just find the x coordinate of the center of mass. Okay. So the generic, unfortunately, I can't do LaTeX in this. That's all right. Okay. Let me switch to draw again. Okay. Nope, too thick. Go back to, this is kind of cool. Okay, the vector r for the center of mass is equal to 1 over the total mass times the integral of r dm. And okay, so that's for us, that's from beginning to end. So here's a little dm here. And so a little pixel of mass. And in fact, it's going to be equal to a little element of dx times the linear mass density. So this linear mass density times a distance, a dx, is going to give you a little bit of mass. Okay. So now we're going to make this simpler. We're just going to do the x coordinate. Okay. And so that's going to be equal to 1 over m. Actually, let me go up here. Let me do this. 1 over m. And 1 over m itself is an integral. And we're going to have to do an integral for it. So for this, it's going to be x times lambda times dx. All right. And so now we have an axis. We can go from 0 to L. Okay, so that's going to be equal to 0 to 0.8. Times x times the linear mass density 0.27. This is painful, but so this is grams. And when you guys are doing this in homework or anything else, oh, you know what? This up here, this is meters here, so let me erase this. This should be 800. Okay, so let's, so this should be 800. Oh, wait a minute, 80. Let me get this back here. Okay, so this should be 80 centimeters. Come on, baby. This thing's blooping on me. Okay, that's better. Come on. Dude. This is burning my grits here. Okay. So this is centimeters, parentheses. Dude. Okay, times dx. So this is equal to, this is burning me here. Actually, you know what? I'm not gonna fool around with this. How about if I just use a little bit of text here? How about that? Okay, so dx, good. All right. So that's going to be 1/2 x squared, et cetera, et cetera. Let's figure out the mass. This one's pretty easy. It's just the linear density. It's a uniform density, so it's just length times lambda. So what is that equal to? Let me stop sharing and share my calculator. Let's see if my calculator comes up here. All right, let's try it again. There it is. Okay. So 800, or no, 80 times, what was it, 0.27? Oops. That's not right. Let's try that again. 80 centimeters times 0.27 equals, so 21.6 grams. All right, so that's, oops, divide one more factor, 10. So that's 0.216 kilograms. So let's go back here now. And let's go back to my, okay, so I'll stop sharing that. And now let me share the whiteboard again. Get back to that. Okay, so this is going to be 0.0, whatever that it was, 216 or something over here. And then I have a 0.267. Okay, so this is equal to, let's see, let me see if I can do this nicely here. Quotient. Okay. And writing. No. Text. 0.27. Divided by, let me move this thing. I can't move this stuff. It doesn't, let me try this. There we go. Okay. Divided by, now what was that calculation? 0.0216. Okay, so down here, kilograms. You know what? I don't like that. Let's just make that. Let's make that 2.16 grams. Okay, and let me move that up here. Okay, so there's your quotient out front. And then you have a 1/2 out in front of that. So let's type in a 0.5. 0.5. Okay, and we'll blaze that up here. Okay, I'll put it in parentheses. Oops. This is painful. I'm sure you guys are already done with this integral. Times x to the tooth. So I'll go x to the second. And then we'll do integrated, evaluated.
It should be 21.6 in the denominator.
21.6. This is 21.6. Is that what I have? Isn't that what I have? Okay, times 1,000. Yeah, 21.6. Okay. Thank you. Okay. X to the tooth. And then, so this is 80. And then down here is 0. Okay, guys, what do we get? I see some chat. Let me check the chat. Okay, 40. Is that right? That can't be right. That seems too easy. Actually, the 0.27 cancels. Does anybody else get 40? Oh my goodness. Dr. B gave a way too easy problem. All right. Okay, so there's that little calculation. Now, it's if you think about that stick, oh, and guess what? That's exactly halfway point. So that's pretty nice. That should appeal to your sense of symmetry. So that's good. And this is similar to the thin hoop. If you have a similar calculation, except you're going 0 to 2 pi on a circle. So, but it works out similarly to that. All right. Now, let's do another page. Oh boy, it's already 11. All right. I want to go through some stuff with you, but when I finished talking about the motorcyclist, I said that there was a analogy between linear motion, i.e. straight line motion and so forth, point A to point B motion, and rotational motion. Now, I want you to think about that motorcycle guy, rotational. The motorcycle guy, if his bike had been a lot heavier, for instance, all right, he'd be on a much smaller parabola, all right, because he wouldn't have the speed to get up into the air. And also it would be harder for him to spin, so he might not be able to do it in the distance given, all right? And so that backflip business might not have been possible. So yeah, whatever he does with a heavier bike, he's still going to follow a parabola. Their center of motion, their center of mass is still going to follow the parabola. So that's squared away. It's easy to do. All right, you just got to know the horizontal component of the velocity and the vertical component of the initial velocity, and you're good. But rotational, center of mass is not the thing for rotational motion. So what I'm going to show you now is something else. Okay, so let me draw an integral. And instead of m times r for the center of mass, so that'll get you the center of mass. All right. You have to sum up mr squared. Actually, let me erase this and put in a summation. Okay, so basically your integrals and stuff are going to look like this. And this is something called the moment of inertia. It's capital letter I, usually. And this is the analog to force, or to mass. This is the rotational analog. To mass. Okay, so for the motorcyclist, the R here, actually I could have done all this in text, I guess. Anyways, this R here, right here, this R, that's relative to some point in that you define in the system. So for the natural point around which to orient, for instance, the motorcycle and his motorcyclist is the center of mass. So this would be the distance to each pixel of mass. So this is from J. Oops, I'm on the. So this is J equals 1 to whatever the number of pixels of mass that you have. Okay, and so each pixel, each pixel is possibly going to have a different mass. Okay, so this needs a subscript. And there we go. And each pixel is going to have a different position, possibly. So that's going to be, let me make that better. That's going to be, it's going to need a J subscript too. So basically, what this goes to in an integral is basically this. It's the integral of r squared dm. And again, you would break this down into, for instance, an integral from 0 to L of, like x squared times lambda dx, for instance. All right, and that's an integral. That one's not too hard, and there's various objects like spheres are fairly easy to integrate. Sticks like this one, and but the thing you have to realize is you have to be very You have to be very careful. Whoops. Oops, I just messed that up. Let me do undo. All right. You have to be very careful of this and the axis that you're calculating about. Okay, so, and the moment of inertia, which is in chapter 10, I believe, we're going to look at it in a minute. That is the rotational analog to mass. So getting something to spin, like the motorcyclist and the motorcycle, it doesn't just depend on the mass, it also depends on how far away from the center of mass the heavy motorcycle is. All right. Same thing for a stick flying through the air. Right now, a stick. Think of a baseball bat. That's a little bit better example. A baseball bat's going to. If you toss a baseball bat from home plate over towards first base, it's going to spin about its center of mass, but that's going to be closer to one end, the heavy end of the bat, than to the handle of the bat. So, but you can also make a baseball bat go in circular motion, like when you're hitting the ball. There, the center of motion is actually, your center of mass when you're holding the bat. So your arms are extended and the baseball bat is extended. And in that circular arc for just a short few degrees of your swing, the center of rotation is, a vertical line probably going straight through your body, straight through the center of your body. So all that stuff is important when you're doing these integrations and stuff. And now I'm going to undo this. I'm going to stop with the whiteboard and let me just do a little bit. I'm going to give you a study assignment. I was going to give you a little more instruction, but I'm going to give you a study assignment. Let's see. Here we go, Safari. Okay, so, all right, so can you see the cube, the two cubes in this? Okay, good. All right, so the two cubes. Now this is chapter 9. Let's go up to chapter 10. Okay, rocket propulsion is, I want you to bypass. Don't worry about 9.7. And, I might get in the chapter review, I think there's some problems in here. Yeah, so there might be some problems here that I think are nice. An elephant chasing a hunter. Now, chapter 10 is about rotational motion and stuff, okay, like these windmills. And so what I would like you to do is to study, and I'll give you some instruction at the beginning of, or maybe in the middle session on Thursday, all the way up to 10.3. And I'll try to annotate some of this stuff. I think the next one. Now, right up to here, this is the analogy table here, okay? And try to study up into all the way through 10.4 for Thursday, and we'll start there. And so that's your study assignment. So there's no written homework, except do work on those problems that I pointed out. See if you could tackle them. Work on those with your group mates, post questions and discussions, and we'll try to attack one or two of them in the first session on Thursday. Okay, you're dismissed. Wait a minute, you're not dismissed yet. Does anybody have a question? Office hours tomorrow. Let's see. Yeah, we can have office hours tomorrow at 7. Okay. We'll go another half hour. I think we went a little bit longer than that the other day. Okay. Anybody else? Questions? Okay, then. Then I'll just wish everybody a pleasant Tuesday, and I'll see you on Thursday.